FSL. This is Mr. Peden. I am obviously not here today, so instead you get to hear my voice over the speakers. I'm sorry I'm not here today. I am at a wedding in Portland, Oregon. I do miss you all dearly, and I do look forward to being back on Monday. I just wanted to start by saying thank you to the substitute teacher in the room. Also, thank you to all of you for being supportive of one another, of the substitute teacher, of everyone in our community to make sure that today is a great day of learning, even despite my absence. So thank you for that. With that framing, I'd love to go over the agenda for today so you know where we're going. So what you are starting to watch right now is an intro to geometric sequences. So we're going to watch this video. You're going to take notes in your notebook, and you're going to be at level 0 for that time. So thank you for that. You're going to be taking notes in your notebook at level 0. After that, you're going to have some time to work on some really cool math problems. And during this time, that is when you can talk with each other. That is the time when you can have some level 2 productive chatter. During the video, please stay at level 0 and make sure you're taking some really good notes. So after the video, again, you're going to have some time to do some problems. The substitute teacher has some great regions problems that they're going to hand out. That they will deal with both arithmetic and geometric sequences. In addition to that, you have homework due today, section 3.2, problems 1 through 12. If you need some support on any problems, there's 1 or 2 that you just still really don't get, know that after the video, you do have an opportunity to work with your team and try to work that out. Try to grapple with that. Remember, without struggle, there's no progress. And remember, with challenges, kind of working through them, that's when we grow our brains the most. So that's due the end of class. And Donovan can collect them and put them on my desk, so I just had those. Again, the other practice problems are really important. They're actually Regents problems. Those are going to be due on Monday. So whatever you don't get done in class today, that will be homework over the weekend. Cool. So that's what we are doing today. Let's do an introduction to geometric sequences. Hooray! I imagine many of you already did this, but if you have not already done this, please take out your graph paper notebook. If you do not have your graph paper notebook in class, it's in your locker, it's at home, whatever it might be. For today, I ask that you make sure to take really good notes on loose leaf paper. I do expect everybody to be writing all this down, and then I'll expect you to transfer that to your graph paper notebook when you get a chance. Please, no one is going to their locker to get their graph paper notebook if it's there. You're going to take notes on your loose leaf paper for today. Thank you for understanding that. If a member of your team needs some support, please offer them some paper for today. In this class, we support one another, and so thank you for doing that. So, knowing all the wonderful students in the room, I would imagine everyone is ready to go. Everyone is ready to take some great notes and see some really cool math. Table of contents update. This is 1.3, geometric sequences. It also says it on the poster in the back of the room. So please update your table of contents and make sure you're including page numbers, because the more math we see, the more important it is that we know how to easily find that. And just another reminder about the notebook. I ask that you do input and output. This is something new that I'm really excited about. So please make sure you're holding yourself accountable to doing this. I think it's a good challenge for us, and I'm excited to see where it goes. On the right-hand side is all the input, the typical notes, your guided examples, your practice problems, your definitions, your notes from reading or videos, in this case. On the left-hand side is the output, the wonderings, the questions, the connections, the predictions, basically your processing space, thinking above the math. What does this remind me of? What am I confused of? You have a whole page for every page with notes to be writing those things. So try to push yourself to writing some questions and some connections in that space. Great, so let's get to it. So this is section 1.3, geometric sequences. Make sure you put a heading on your notes, and go ahead and write down definition of a geometric sequence. So the definition is a sequence, for example, a sub 1, a sub 2, a sub 3, dot, 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 goes on forever, infinite sequence, is a geometric sequence if there is a constant r for which a sub n, remember that denotes just kind of like the nth term, if a sub n can be found by taking a sub n minus 1, which remember is the term before a sub n. Okay? So if you take the previous term and multiply it, interesting. So now we're talking multiplication. If you multiply it by some constant each time to get to the next term, that is called a geometric sequence. We did arithmetic. Remember, it was adding the same number every time. In that case, it was called a common difference. In this case, it is called a common ratio. So we use R for common ratio. And if you have a geometric sequence and you want to find that common ratio, you can take any term, call it a sub n, and simply divide it by the term before it, a sub n minus 1. So if you have a geometric sequence, you can always find what that common ratio is by taking any term and dividing it by the previous one. That'll tell you what you're multiplying by each time, what that common ratio is. I would imagine everybody has this down at this point. You can always pause the video if you need a few more seconds, but hopefully you're good, so let's keep moving. Actually, let me rewind for a second. I apologize. This here is actually a recursively defined formula. Recursive, wow, I did not write. Don't write that. This is recursive because to determine any term, you have to know the previous term, the term before it. So that would be defining a geometric sequence recursively. But what if you wanted an explicit formula? Similar to arithmetic, there is a pretty easy explicit formula for geometric scenarios. So the explicit formula is as follows. The general nth term of a geometric sequence, called a sub n, with first term, called a sub 1, and common ratio r, may be expressed explicitly as a sub n is equal to the first term, a sub 1. So this is your first term, remember, multiplied by r, which is the common ratio, to the n minus 1 power. Remember, raising something to a power is like repeated multiplication. So you're just multiplying by r n minus 1 times to get to the nth term. You're taking the first term, multiplying it by the common ratio, n minus 1 times, to get to the nth term. That may or may not have made sense. Either way, let's do an example so it'll really kind of sink in. So there's some questions for your output page. You can hold off on those for a second if you want. Let's see an example. So example, consider the following sequence: 2, 6, 18, 54, 162, 486, and copy these questions down in your notes as well as the actual problem. Question 1 says, is the sequence arithmetic, geometric, or neither? Let's test arithmetic first. Recall, arithmetic means there is a common difference, which means you're adding the same number every time to get to the next term. So, let's take a look at this. 2 to 6. To get from 2 to 6, you would have to add 4, right? Because 6 minus 2 is 4, so 2 plus 4 gives us 6. So what if we added 4 to 6? Wait a second. Is 6 plus 4 18? No, I'm pretty sure it's 10. Which means what? It means that this sequence is not arithmetic. There's not a common difference. Let's try geometric. Okay? Geometric means there would be a common ratio, meaning you're multiplying by the same number every time. So you get from 2 to 6, well, 6 divided by 2 is 3. So you get from 2 to 6, you would multiply by 3. To get from 6 to the next term, let's see. What if we multiply by 3 again? Is 6 times 3 18? Absolutely. 18 times 3, let's try this one, is 54. This is looking pretty good. 54 times 3 is 162. 162 times 3 is 486. I think we found what kind of sequence it is. It is on a geometric sequence. Okay? It's a geometric sequence because there is a common ratio. Now, looking back to your notes, let's write, I'll keep the sequence in the screen. Let's write a recursive and an explicit formula to describe this sequence. So recall, in general, for a geometric sequence, a recursive formula would look like this. A sub n is equal to the previous term, a sub n minus 1, multiplied by some common ratio. So that's just the general recursive form for a geometric sequence. Let's plug in the specific values for this. Okay? What is our common ratio? Well, our common ratio is, we discovered it was 3. So 3 times a sub n minus 1. Basically what this means is the nth term can be found by taking the previous term, a sub n minus 1, and multiplying it by 3. The problem with this, though, is where do we start? If you just wrote that, you would have no idea where you start this sequence. So when we define things recursively, we also need to give some additional information that tells the reader, the mathematician, tells the person that, tells them where we start. So in this problem, we have to know the first term in order to really define the sequence. The first term is 2. So altogether, that is one way to define this particular sequence. We know we start at 2 and we multiply by 3 every time to get to the next term. So that's our recursive. Okay? That's a recursive. Now, let's talk about explicit. So explicit, in general, the formula we just wrote down was a sub n is equal to, well, we can take our first term, which I'll do in blue, let's say, a sub 1, multiplied by the common ratio, which I generally write in red, to the n minus 1 power. So that's just the general formula general explicit formula for any geometric sequence. But in this case, we want to specifically define this one. Okay? So we're going to plug in those values. We already know the first term is 2, right? The first term is 2. So let's plug that value in. The first term is 2. And our common ratio we already know is, whoops, that's erased, is 3. Okay? So 2 times 3 to the n minus 1 power. That is a way to define this sequence explicitly. There we have it. The nth term of the sequence can be found by taking 2 and multiplying it by 3 n minus 1 times. Okay? So, number 3. Use the explicit formula. Apply the explicit formula we just developed to determine the 12th term of the sequence. That's not too bad. All we need to do is plug 12 in for n. So we have this formula. The nth term can be found by plugging in n into this formula, taking 3 to the n minus 1 power, and then multiplying it by 2. So a sub 12 is what we're trying to determine here. The 12th term of the sequence is going to be equal to 2 times 3 to the 12 minus 1 power. Okay? 2 times 3 to the 12 minus 1 power. Well, 12 minus 1 we all know is 11. So this is like saying 2 times 3 to the 11th power. And thinking of order of operations, gems. There's no grouping symbols, so we're going to do exponents next. And then we'll do the multiplication. So we're going to do 3 to the 11th power. Sorry about that. 177,147, hopefully that's correct. Times 2, it should be 356.